You've probably imagined it before, lying in the dark, half asleep, staring at nothing. What would happen if you fell into a black hole? Most people picture a giant cosmic drain, sucking everything into oblivion. But the real answer is far stranger than that, and it depends entirely on one thing: the size of the black hole you fall into. Start with the small ones. A black hole with the mass of our Sun squeezed down to about 6 kilometers across. You approach it feet first. Your feet are closer to the black hole than your head. That tiny difference in distance means gravity pulls harder on your feet than on your head. Not by a lot, but enough. This is called a tidal force. Every planet and star creates one. The Moon does it to Earth's oceans, which is why we have tides. But a black hole's tidal force, close to its center, becomes monstrous. Your body starts to stretch, your feet accelerate away from your head, faster and faster, until you are pulled into a thin, glowing strand of matter, no wider than a strand of spaghetti. Physicists actually call this spaghettification. It's not a nickname invented for television, it's the real term astrophysicists use in published papers. Would you feel it happening? For a small black hole, yes, painfully and fast. Within a fraction of a second near the smallest stellar black holes, the forces would be strong enough to tear you apart before you ever crossed the horizon. There would be no time to reflect on the moment, no time to look around, just an instant, violent unraveling.
But here is where it gets strange. Not all black holes behave this way. Picture a black hole millions or even billions of times the mass of the Sun, the kind that sits at the center of most galaxies, including our own. The one at the center of the Milky Way is called Sagittarius A star, and in 2022, the Event Horizon Telescope collaboration released the first image of it, a faint glowing ring around a dark center. That image existed because of years of work by hundreds of scientists, including Katie Booman, whose imaging algorithms helped turn raw radio data into a picture humanity had never seen before. A black hole that size is so large that its tidal forces near the horizon are actually gentle. Counterintuitively, the bigger the black hole, the smoother the fall. You could, in theory, cross the event horizon of a supermassive black hole without feeling anything unusual at all. No stretching, no tearing, just space, and then more space. That's the part most people never expect. The event horizon isn't a wall, it isn't a membrane you'd bump into. It's simply the point past which nothing, not even light, can escape. You wouldn't see it coming, you wouldn't feel yourself cross it, you would just keep falling. So what happens after that? This is where physics starts arguing with itself. Albert Einstein's general relativity, refined mathematically by Carl Schwarzschild just months after Einstein published his theory in 1915, describes a singularity at the center. A point of infinite density, where the equations simply break down and stop making sense. Roger Penrose, who won the Nobel Prize in Physics in 2020, proved mathematically that singularities are not just possible, but an unavoidable outcome once a star collapses past a certain point. His work showed that once you cross the horizon, every possible path you could take, no matter what you do, leads to the center. There is no escape route, not because of speed, not because of fuel, but because inside the horizon, the geometry of space itself only points one way. Falling toward a singularity sounds like the end of the story, but there's a version of the ending that's even stranger, and it comes from Stephen Hawking.
Yet Hawking's own equations seem to suggest it does. This became known as the black hole information paradox, and physicists are still fighting about the answer today. Now, think about the view. If you were falling toward a black hole and somehow survived long enough to look around, you wouldn't see darkness closing in like a tunnel. You would see the entire universe compress into a bright ring above you, light bending around the extreme gravity, stars you'd never noticed twisting into new positions. Time itself would look different depending on who's watching. To someone observing you from far away, you would appear to slow down as you approached the horizon, frozen there forever, your image growing dimmer and redder until it faded from view entirely. But from your own perspective, nothing would feel slow at all. You would cross the horizon in an ordinary instant and continue falling, unaware that outside observers believe you never made it. Two versions of the same event, both true, depending on where you're standing. That's not a metaphor. That is what Einstein's relativity actually predicts. Why does any of this matter to someone who will never come within 1,000,000,000,000 miles of a black hole? Because black holes are the sharpest test case physics has ever found. They force gravity, the force that governs galaxies, and quantum mechanics, the theory that governs particles, into the same tiny space. And the two frameworks that explain almost everything else in the universe start to contradict each other. Somewhere inside a black hole, or perhaps at the horizon itself, lies the seam where our two best descriptions of reality don't fit together. Understanding that seam is one of the last great unsolved problems in physics. There's something oddly personal about that. You spend your life assuming the ground beneath you is solid, that time moves at the same pace for everyone, that cause always comes before effect. A black hole is the one place in the universe where all three of those assumptions quietly fall apart, not through some exotic technology or alien intervention, just gravity taken to its most extreme conclusion. You will likely never fall into a black hole, but in a smaller sense, you already understand what it feels like to approach a horizon you can't see the other side of, a decision with no way back, a moment where the outcome is already fixed, even if it hasn't happened yet. Physics just gave that feeling a name, a location, and an equation. So the next time you're lying in the dark, half asleep, wondering what it would be like to fall into a black hole, remember this: the stretching, the silence, the strange bending of light. None of it is the strangest part. The strangest part is that somewhere out there it's already happening to someone, right now, and from where you're standing, you would never even see them go.